Welcome. In the last class, we have discussed about vector space and vector subspace. We tried to discuss about their definitions and looked into few examples, and we also looked into column space and null space. These two spaces are associated with matrix A and solution of matrix A x is equal to 0. And we observed that these are also vector subspaces. Subspaces in the sense they follow the rules of vector space within a larger vector space. For column space, it has the larger vector space has a dimension R m, where R is the real coordinate space, and R n, and for null space the dimension is n, where dimension of the larger space is n, or real coordinate space is n. So, today we will start looking into the use of the ideas of vector space in solving equations A x is equal to b in cases where A x is equal to b does not have a unique solution. In case they have unique solution, we can use Gauss elimination or LU decomposition or Gauss Jordan, the standard method to solve the equation. However, in cases they have infinite solution, these methods cannot be utilized. So, in today's class we will see few examples through which we can solve cases where x is equal to b can be solved where x has multiple solutions. We will start with finding null space of such matrix A, which is a singular matrix, so that x is equal to 0 has multiple solutions. We will discuss about these things. So, the topic for today's class is finding null space of A and solving x is equal to b when A is not invertible or A is a singular matrix, so that we cannot use Gauss elimination type of method. The definition of null space, I tried to give it in the last class. Null space of a matrix consists of all vectors x such that A x is equal to 0. It is denoted as n of A. So, if I have an equation A x is equal to 0, if it is not a singular matrix, there is a trivial solution x is equal to 0. In case it is a singular matrix, there are infinite x's possible. So, all these solutions for a singular matrix only x is equal to 0 consists the null space. For a non-singular matrix, for a singular matrix, all the solution which satisfy x is equal to 0 will consist the null space. And null space of a matrix A which has order m into n is a subspace of real coordinate space of dimension n or R n. So, if n is the number of column or number of elements in the row, that is the dimension of the real coordinate space R, to which null space is a subspace. So, we consider the equation A x is equal to 0. A again is a matrix of order m into n. If n is equal to m, number of equation is equal to number of unknown, and we can write x is equal to 0. We can look into a simple example like x plus 2 y is equal to 0, and maybe 4x plus 5 y is equal to 0, and the only solution possible is x is equal to 0, y is equal to 0. But if we take another example where number of variables is greater than number of equations. So, we will write only one equation x plus 2 y is equal to 0. Then the equation is basically x is equal to minus 2 y. So, all this solution x is equal to 1, y is equal to minus f, x is equal to 2, y is equal to minus 1, x is equal to minus 2, y is equal to 1. All of them are solution to this equation. So, all these vectors 1 minus 2, 2 minus 1, minus 2 1, and of course, x is equal to 0, y is equal to 0 is also a solution. All these consists what is they belongs to what is called the null space. Now, if number of equation is equal to number of unknown, null space is usually 0, only that the equation should not be repeating. So, we can have another case like x plus 2 y is equal to 0, the second equation is 2x plus 4 y is equal to 0. So, then if I look into the matrix A, this is 1 2 2 4, and this is a singular matrix, determinant of A is equal to 0. It will also have a null space which is not only 0, which has vectors more than the 0 vector. but if the equations are like this, that there are two independent equations, then the null space will be only 0. So, if A is a singular matrix, we will have null space which is 0 plus something, but if A is a full rank matrix, null space will be only 0. So, again our intention is to find out null space for singular matrices where it is 0 plus something, and we will see 0 is a member of null space, what are the other members, so that we can say how the other solutions of of x is equal to 0 are behaving. How does it look like if I look into all solution of x is equal to 0 in case A is a singular matrix. So, we will go through it in next few slides. How is null space? For example, I have a matrix A 1 5 2 0 4 4 1 9 6. So, I can make an observation here. If this is column 1, this is column 2 and this is column 3, column 3 is equal to column 1 plus column 2, right. 1 plus 0 1, 5 plus 4 9, 2 plus 4 6. So, this is a singular matrix. If now I have the null space equation A u v w is equal to 0 0 0. So, u v w will belong to null space of A. What will be the solutions? By inspection we can see one solution is 0 0 0, that will be definitely one solution, and another solution is 1 1 minus 1. So, first column into 1, because third column is sum of first and second column. So, first column into 1 plus second column into 1 and third column into minus 1 is another solution. Similarly, another solution can be 2 2 minus 2, 2 into 152 plus 2 into 044 minus 2 into 196 is equal to 0. So, all these will be a solution, and null space will be finally a line which passes through origin and 1 minus 1. So, if I think of a 3D geometry and this is the point say x, y and z, this is my point 1, this is 1 and this is the point somewhere 1 minus 1, the null space will be this. Any vector pointing to any point on this line will be a null space vector. However, this is a simple matrix and we can find the null space by inspection only, that first and second column can be summed up to get third column. So, any vector which any solution which multiplies 1 with first column, 1 with second column and minus 1 with third column or multiplier of that will be a solution. My question becomes how to find out null space for a larger matrix or for any general matrix where we cannot do make inspection, simply inspection based decision on solution in as that simple as we have done here. The next important thing is that we can see that the null space here is a line, straight line. So, we will know that though x is equal to 0 has infinite solutions, all these solutions will fall on that particular line. And if someone is interested on solving some case where probably only first two columns are available. So, I have 3 variables and 2 equations, I can still say that all these 3 variables will fall on that particular line. These informations can be important in several applications where we cannot form the entire equation set for all the variables, still we have an idea how the variables are behaving based on fewer equations. However, we will now try to look how the null space behaves and what is its importance in case we try to solve Ax is equal to b. From Ax is equal to 0, which is the null space equation, if we try to solve Ax is equal to b, and which is not a null space, x does not belong to null space when we are solving x is equal to b. The importance is that if A is a singular matrix, x is equal to 0 will have infinite solution, also x is equal to b will have infinite solution. So, if I try to find out how infinite solutions of x is equal to b look like, I can probably utilize the fact that I already have made an idea of x is equal to 0. So, we will try to find out null space first and then we will see how we can utilize this to find out x is equal solution of x is equal to b. Non-unique solution of x is equal to b is possible when A is rectangular. That means, we do not have enough equations to find out all the variables uniquely. What we are looking here, non-unique solution is possible if A is rectangular or A gives 0 pivot during Gauss elimination or A inverse does not exist. So, these three conditions, if I see, two conditions rather, if we see that A is rectangular, we do not have enough equations to find out all the variables uniquely. Like earlier case, one equation was dependent on other. So, we did not have enough equation to find out all the variables uniquely, or the matrix is itself singular. If I again if we look into the previous matrix, if I try to form a Gauss elimination, after 2-3 steps we will start getting 0 pivots which cannot be eliminated. So, or both cases A inverse cannot be found out, so that I cannot uniquely find out x is equal to A inverse B, because A inverse cannot be found out here in this particular case where Ax is equal to B has a non-unique solution. A inverse cannot be found out here, because A is a singular matrix or a rectangular matrix. So, then if we try to solve Ax is equal to B, we can divide Ax is equal to B as Axp is plus Axn is equal to B, or we will write x is equal to Xp plus Xn, and Axp can be equated with B, Axn can be equated with 0. So, Axn is equal to 0 will be a null space equation, and Axp is equal to B will be something else, not a null space equation. And we can therefore break, when Xp will call it a particular solution, it is the solution of Xp is equal to B, it does not contain the null space, and Axn is the null space vector. So, Axn is equal to 0 is a solution, is the equation which we are solving to find Axn. So, these two we can break down Ax is equal to B into these two equations, and can distinctly solve X equal to P, Xp is equal to B, the particular equation solution in one equation, and the null space equation Axn is equal to 0 in another as another equation. The advantage of doing that is Axn is equal to 0 will give me how these infinite solutions will behave, and we will get one solution of Axp is equal to B, right. We cannot directly get it through a technique like Gauss elimination, we have seen it earlier, because A inverse does not exist and it will give 0 pivot. Still, we will see some method through which we can get one particular solution of Axp is equal to B. So, this will give me one solution, and this will give me infinite solutions. So, this there is one Xp and there is infinite Xn, all belonging to null space of A. Therefore, as X will get infinite solutions. That is the goal of this exercise, that I have an X is equal to B where A is rectangular or A gives 0 pivot, A is not a full rank matrix, A inverse does not exist. So, X is equal to B will have infinite solutions. So, what should I do here? I will try to find out infinite solutions of X is equal to B. I will take Xn is equal to 0 in the null space equation, from which I will find out infinite Xn, infinite types of Xn all belonging to null space, and I will solve Xp is equal to B, which will give me one particular solution. For certain condition I will give one solution which is satisfying Xp is equal to B, and then I will add those things and say that X is equal to Xp plus Xn, and this gives me this infinite solution. In differential equations we often use this technique, we find the solution to homogeneous equation and we find out the solution to particular equation, and we say that this is the final solution which contains both the homogeneous part, this is null space part here, and the particular integral part which is particular solution here, and we will follow these steps in next few slides. Axn, Ax is equal to B, non-unique solution. This case, once we try to find out the solution of Axn is equal to 0. This is always solvable, it might have trivial solution and infinite solution. And why is it always solvable? Because 0 all subspace, 0 belongs to any subspace. So, 0 vector is also a subspace of column space or member of column subspace. 0 vector is a member of column space. Any subspace or any vector space must contain 0 vector. Therefore, 0 must belong to the column space, and Ax n is equal to 0 will always have a solution. Ax p is equal to b is critical. It will only have a solution or multiple solutions when B belongs to column space of A. If B does not belong to column space of A, this cannot be solved, and we will look into an example where we can solve Ax n is equal to 0, but we will not able to solve Ax p is equal to B, and we will stop that this system will not have any solution. In order to solve this equation x p is equal to b or x n is equal to b, when I do not have a full rank matrix A is a singular matrix, A's determinant is 0, we will try to get echelon or reduced to echelon form with pivots in non-diagonal locations. So, what is it? If we see the echelon form, it is like a step form. The idea echelon, we discussed about reduced to echelon or echelon matrix when discussing Gauss-Jordan steps. Gauss-Jordan steps takes a matrix A and gives its reduced to echelon form. So, echelon the terminology echelon came out from how to arrange soldiers in a battlefield, and it is a step like arrangement. There will be zeros arranged in steps, and above 0 in any step there will be non-zero number. So, this is a non-zero number, this is a non-zero number, all these black dots are non-zero numbers, and these stars can be anything, it can be a 0, can be a non-zero. So, what is this matrix actually? If we think of getting an upper triangular form through a pivoting, we started, this is a one pivot point. Let us say have some A matrix and started Gauss elimination step. This is one pivot point, here the pivot becomes 0. So, the next point becomes a pivot here. The diagonal element is not a pivot, because it is not a full rank matrix, and we will in standard lower triangulation or Gauss elimination technique we are getting a 0 pivot here, the next term is probably non-zero. Similarly, we get next one 0, next few terms 0 and a non-zero here, and we will of course, because the pivots do not exist at diagonal location, they will finish before the last row, and we will have few rows which are completely 0 rows. And this matrix can be converted into a reduced to echelon form, like for example, if I divide this by, say this has a value 3, if I divide this matrix by this row, the matrix by 3 or this row by 3, this will be 1, and we get a reduced to form, and then we will subtract this 1 with multiplied by suitable multiplier with all these terms, and we will get all these terms to be 0. There can be in the non pivoted columns, there can be some non-zero terms. So, these can be 0 or non-zero, any term, and then we will get a pivot which is 1, because it has been divided by the value its value in echelon form matrix, and the above terms are 0. So, this what we will call a reduced to echelon form, and the idea of reduced to echelon form is that the first term coming from left in any row is 1, the first term is 1, and the terms in one particular column above this 1 are always 0. So, we will find an 1 which has above term 0 and the left term 0 at any column row position, and then there will be a step like arrangement, and this is called a reduced to echelon form. We have seen that in MATLAB or in many computer programs there are functions which you call rref, which will take a matrix and give its reduced to echelon form. And A, if we can remember of Gauss-Jordan method, it takes any A and converts it to R or reduced to echelon form through matrix exercise, or we have written that M A is equal to R, where M is matrix operation, matrix operations. M is a matrix combining different matrix operation like subtracting a row from other, multiplying a row by a constant, dividing a row by a constant, etc. So, if I multiply M with A, we will get R or reduced to echelon form, and we have seen it in Gauss-Jordan method. Why is it important? We will come in a while, because this gives us matrix which are like a pivoted matrix, but with 0 pivots. And if I have a singular matrix and I try to follow Gauss-Jordan steps or Gauss elimination steps, I will get a matrix like this. Gauss elimination step will fail here, because it will see 0 at the pivot locations. So, the Gauss elimination method will fail here. However, this is what we will get out of Gauss elimination steps in a singular matrix, and we will use this to get the null space solutions. So, we will take the example 1 3 3 2 2 6 9 7 1 minus 3 3 4 u v w y 155 is equal to 155. This is a rectangular matrix, so it is not invertible, and we cannot utilize Gauss elimination step here to get solutions, and there are, we can see in total 3 equations and 4 variables. So, it has to have infinite solutions. So, let us see how to find out the solution of this equation, and we will first look into null space equation. We will find out the null space solution first, and then we will find out the particular solution and add them and say this is the final solution. So, the null space solution is 1 3 3 2 2 6 9 7 minus 1 3 3 4 u v w y is 0 0 0, and we will see how can we find the null space. So, this is the my null space equation. I do a row operation to eliminate the first term of the second row, because my idea is to get a reduced to echelon form here. So, there will be a 1 1, and if this is a 1 here, the terms that there will be another 1 here, and the terms left to it will be 0, something like that. So, I will try to eliminate the first column term from the second row. So, and this is very similar as Gauss elimination steps. Second row is first row, second row will be second row minus twice of first row. So, these terms are eliminated. The next step is third row is third row plus first row. So, first term and the second term is also eliminated. See, when we are trying to eliminate the first term of second row, the second term of second row, which is ideally a pivot term in a Gauss elimination step, is eliminated. Okay, we are not trying to get a upper triangular matrix, we are trying to get a reduced to echelon form matrix. So, this will work. So, the next step is, what will be the next step? I will try to eliminate the third term of third row, or I will try to see how many zeros I get eliminating in the third row. So, twice of third row, second row will be eliminated from third row, and we will get a 0 here. Now, I got something close to a reduced to echelon form, rather I got what is called an echelon form. I got an echelon form of matrix. This is not a step form of the matrix, this is not a reduced to echelon form. So, what I have to do? I have to divide this 3 by 3. So, this is 1, this row by 3, and this row is already, the pivot is 1 here. So, the next step is, well, I have to also eliminate the, if this is the pivot term, the above terms will be eliminated. So, first row is eliminated by, first row is formed as first row minus second row, and this term is 0. So, this now can be a pivot in a reduced to echelon form matrix. I divide by second row by 3, and first row is already, the first term is 1. So, this is what I get as a reduced row echelon form. This is a step like form, echelon form. The first term in any row, first non-zero term in any row is 1, if I have a non-zero one term pivot term in any row, the above term is also 0. So, this is a reduced to echelon form. The right hand side vector remains same as it is 0. We have done many matrix operations because, but this, as this is the null space equation, the right hand side always remain 0. So, Ax is equal to 0 is same as Rx is equal to 0, where R is the reduced to echelon form of A. This was the initial Ax is equal to 0, and this is what we are getting in the new reduced to echelon form matrix Rx is equal to 0. And now we will see how we can find out UVWY or the null space solutions by through this reduced to echelon form of matrix, and we will look into it in the next class. Thank you.